about quantum scars.
Okay, first of all, I would like to thank the organizers for inviting me here. And I'm sorry about this, but I just gave this same talk, almost the same talk 2 weeks back in the same hall. So, but you know, the audience is quite different, but I'm particularly happy to torture the chair who was there in that talk. So, but okay, to start with, so I'm going to talk about some quantum scars in Rydberg ladders with staggered detuning. And in the event that I don't get to finish the entire part of it, let me just tell you the main result. What we found is that these scars are very different from their well-known counterparts in the chain. As you know, in the Rydberg chain, these quantum scars are very well-known and they have been experimentally found. And the idea of this work is to highlight this difference. So this work is done with a few collaborators. So Moinak Pal, who is a student at ICTS Kolkata, working with Arnav Sen, who is my colleague at ICTS Kolkata, and Madhumita Sarkar, who is now in UK, and she was a student in our group when this work started, and then she moved during this. And this is the archive if you want more details. So first I'm going to talk a little bit about Rydberg chains and then go to ladders, talk about ETH, that is eigenstate thermalization hypothesis, and how it can be violated by scars. And then come to the main topic, which is scars in these staggered ladders. And what I'm going to show is that these scars lead to, first of all, site-dependent dynamics, even in the long time limit, and give rise to a long time imbalance, even when there is no disorder in the system. And this, I think, is one of the central points of our work, that this leads to a scar-induced imbalance, even when the system is not MBL, it doesn't have strong disorder or anything like that. Okay. And then I'm going to discuss, if time permits, the role of chirality operators behind these scars and this imbalance. And finally, there are some simultaneous zero energy states which are quite interesting, which is found in ladders but not in chains, and I'm going to talk about that. Okay, so here is the experimental system. You have a bunch of Rydberg atoms which are, subjected to this Raman lasers. And this system of Rydberg atoms are controllably coupled to their Rydberg excited state. Now, in the excited state, there is van der Waals interaction between these two atoms, and this is denoted by V in here. So this V, its amplitude, V naught, is a tunable parameter, and it can be tuned so that the Rydberg excitation in neighboring sites or a few neighboring sites are forbidden. This phenomenon is very well known. It's known as Rydberg blockade. In addition, one also has a detuning parameter, which is just the chemical potential, which tells you how easy or hard it is to excite a Rydberg excite an atom to its Rydberg state. So these are the atomic details of the state. So typically an atom is in the ground state, and then there is this Rydberg excited states, and these are coupled by these two lasers. Okay. And also there is an effective term which couples between this the ground and the Rydberg excited state. And if you put all of this into a black box and churn a little bit, out comes the Hamiltonian, which is this detuning term, the interaction term, and this coupling term. Okay. And since there are just two states per site, one can write a spin representation for this. Here n is the number of Rydberg excitation, and that is related to sigma z by this 1 plus sigma z by 2. And the Rydberg excitation is typically 1 over r to the power 6. Okay, that's standard. So Michel Luquen's group has done a lot of experiments with this, and one of the central things that they did is to tune this Rydberg, tune this V naught to a really large value, so that when this detuning is large and positive, one finds a Z2 ordered state. That is, when the detuning is large and positive, every site wants to basically create a Rydberg excitation, because that's energetically favored by this detuning term. However, because of this interaction term, it can only do that at neighboring, next nearest neighboring sites. So this leads to a Z2 ordered state. If you increase the interaction a lot more, when Rydberg excitations at two neighboring sites are forbidden, you can get to a Z3 ordered and so on. Okay, and the Rydberg vacuum is a state at small detuning or negative detuning, where these Rydberg atoms are preferentially in their vacuum state. Okay, so these states, one of them breaks a discrete symmetry, the other one doesn't, and therefore these are separated by a transition. This transition happens to be in the Ising universality class because there is a Z2 symmetry involved. And this is very similar to some transitions that we found long ago in tilted optical lattice. The physics is not very different. So one way to tackle this Rydberg problem theoretically is to map it into a constraint model. So what happens is that instead of treating this excitation using this term, one can think of using a projection operator which just takes into account that Rydberg excitations in neighboring sites are blocked. So in terms of the spin model, upspin, you can go into an upspin state only if the neighboring two sites are down. That is, you can go into a Rydberg excited state only if your two neighboring atoms are in the ground state. And therefore, you can implement that by putting the projection operator like this. And this Hamiltonian in the limit of strong Rydberg blockade essentially reduces to this PXP model plus a magnetic field. Okay. So this transformation works. And in fact, it is this model that we are going to use for the rest of our talk. Okay. So now let me change gear a little bit and introduce the concept of eigenstate thermalization hypothesis, although this is probably unnecessary for most of the people here, but let me go ahead and do it anyway. So when we consider a generic state in a quantum non-integrable many-body system, I can take that state and write it in the eigenbasis. Okay, so like this, where C is the overlap coefficients. Now, when I try to calculate an time evolution of a generic operator, generic local operator, I find that it's easy to see that this is the answer, where this OMM are the matrix element of the operator O between the eigenstates M and N. Now, the point is that this answer essentially poses two problems. The first is that suppose I just look at a very, very long time where these off-diagonal terms can be neglected, then one finds that the steady state value of O of t depends on the overlap coefficient. In other words, it retains its memory. And this is completely different from what we actually expect from statistical mechanics, where you expect thermalization. The second problem is that you can ask that how long is this time? And within this, it should take an incredibly long time to reach this steady state, because you can neglect this term only when this time is large enough compared to the inverse of this spacing. And this spacing in the middle of the spectrum is quite small. It's exponentially small in system size. And therefore, this time is exponentially large in system size. And that's not what you typically see in an experiment. Relaxation times are typically order 1 timescales. So invoking random matrix theory, which predicts that these matrix elements, OMM, essentially has the following form: OMM is equal to some number and OMN is 0, remedies both of this problem, but it provides an energy independent answer, which is again not something that you see in standard statistical mechanics. So eigenstate thermalization hypothesis essentially tells you that it's a generalization of this random matrix theory result excuse me, where the matrix element, the form of the matrix element is essentially taken to be this. The diagonal elements depends on some average energy, and off-diagonal elements essentially suppressed by this, this entropy factor, which is extensive. Okay. And I'm not going to get into the details of this, but once you put this thing in and calculate this long time average, you see that everything is fine. And relying on the fact that energy fluctuation in a many-body system are sub-extensive, one can show that this goes to a diagonal ensemble, which is basically same as the microcanonical ensemble, because the difference is just some energy fluctuation terms which are sub-extensive. This can be done, and this review article by D'Alessio, Polkovnikov, and Marcus Riegel, that explains it very well. Okay. However, this eigenstate thermalization hypothesis can be violated whenever ergodicity breaks down. And one way to do that is to study integrable models, where there are a large number of constraints which breaks this ergodicity. The other one is many-body localization, where very strong disorder makes you localized in Hilbert space and therefore breaks ergodicity. But today I'm going to talk about violation of ETH due to the presence of a special class of eigenstate in its Hilbert space, which are these quantum scars. And this is going to be a weak violation of ergodicity because in this case, when you start from an initial state and study the dynamics, ergodicity, the breaking of ergodicity will show up essentially only if, the violation of ETH is going to show up only if that eigenstate has a good overlap with this special class of states which are quantum scars, okay? Not otherwise. So it's a measure zero state which violates this ergodicity, but nevertheless it is violated. So what are these quantum scars? So I'm going to give you a very brief example of what this is. That's just for my purpose of introducing scars in the Rydberg chain later on. So think of a spin 1 chain which has a XY term like this and Z and a magnetic field. Now there are two polarized states which are eigenstates of the model. One is that it's a ferromagnetic state with all spins down, and remember that this is spin 1, so you can have minus, plus, and 0. So say we start from these states, then typical excitations could be a single Magnon states, which is obtained by applying the spin raising operators, which creates a 0 from minus at one given site, and then that 0 can keep on propagating, which gives you this Magnon dispersion. But there are another class of states called the bimagnon states, which is obtained by repeated application of this J plus minus operator, which is application of two S plus or two S minus operators on this chain. So suppose I start from this minus minus state and I apply this S plus minus, so S plus operator on one of the sides. So it gives you a 0 out here, okay? However, now when this term acts on it, it produces, so it gives you a plus on one of the side and minus on the next side. Now when this HXY acts on that, it gives you a 0-0 pair. But depending, because of this e to the power I pi r factor, depending on whether you are creating the plus on an even side or odd side, these 0-0 pairs comes with different signs, and therefore HXY completely annihilates that state. And therefore, the energy of these states essentially is the number of flipped spins, which is this H2n minus L, and this gives rise to a star of states, and is an example of a spectrum generating algebra, where omega is just this En. Okay, these bimagnon states is a separate star of states, and the reason it violates ETH can be understood in the following manner. That suppose you take these states, okay, and you take these operators, you'll find that they form an SU2 algebra, that is, they form a spin L by 2 representation of an SU2 algebra. And this, therefore, there is an emergent SU2 symmetry out here, and this symmetry essentially do not allow the states to hybridize with other thermal states in the system. And this leads to completely different value of different correlators and entanglement, so there are some answers out here, and more is given by this review article by Anusha and Vedika and others. So essentially, there is this, once you are inside this subspace, there is coherent oscillatory dynamics and not the standard ETH-based thermalization that you see. So now let me, with this introduction, let me come to scars in Rydberg chains. And these scars essentially have this oscillatory structure which comes from, which was seen in experiments in Rydberg chains. And essentially these are controlled by this set of states which are athermal. The dynamics do not show thermalization up to very long times. And very long times here means in system time scale, which is long in terms of this Rydberg chains. And however, this oscillation time scale is finite. You eventually go to this steady state value, which is not exactly the thermal value predicted by ETH, but some superthermal value, and that happens because there is leakage to the thermal state. Here it turns out that the scars do not satisfy a perfect SU2 algebra. This SU2 algebra is approximate, and there is a leakage term. But barring that, it's really the same physics. And this dynamics, which you see here of, let's say, expectation of magnetization or some such stuff, starting from an initial nil state. It can be approximated using a technique called the forward scattering approximation as coherent revival between two Fock state, the nil and its time revert partner, which we commonly called as Z2 and Z2 bar. Okay. So this is also an approximate picture, but it more or less gives the correct understanding of this kind of scarce states. So now, with this background, let me come to scars in the ladders. Okay. So the first thing that we want to do is we take these ladders with the following Hamiltonian, that we want to introduce a ladder which is this staggering term. Okay. So here the detuning in our case is staggered with its -1 to the power j factor, and the rest is basically the same projection operator. Here the only difference is that in this, once you put in a term which is an upspin, or rather Rydberg excitation on any of these, the neighboring sites, which involve sites both in the same rung of the ladder and the opposite one, cannot have a Rydberg excitation. Okay, so then the projection operator is designed accordingly. So the first thing that we do is that we study this thing at delta equal to 0, where it's just the PXP model generalized to this ladder geometry. And here you see that there is a large oscillations provided we start from the nil state. And if we start from other states, which is Z3, Z4 or vacuum, which are one spin flip with two down spins, one up spin with two down spins, that kind of stuff. And the vacuum is of course all down spins. We don't see any oscillations. When we increase delta, keep on increasing delta, this oscillation dies, and around delta equal to 0.5, everything follows ETH. However, the oscillations reappear once you go to delta equal to 1. And here, both the Z2 and the vacuum states show steady oscillation. And that's the first indication that the scars at delta equal to 1 are completely different from their delta equal to 0 counterpart, because they have an overlap with the vacuum state as well. And notice that the vacuum state shows a subthermal value, whereas the nil state shows an superthermal value, average value, out here. So evolution as a magnetization density as a function of time first gives you this first indication. But the second thing is, which is really interesting, is this local magnetization dynamics. So here I take a given placket of this ladder, and these are the index of the sites. So this is 2j minus 1th site of the first ladder, 2jth site of the first ladder, 2jth site of the second ladder, and 2j minus 1 site of the second ladder. And I study this local magnetization at every site for both the longitudinal and the transverse component. So here, it seems that spins at different sites converge to either superthermal or subthermal values at long time, and this is the key to generating imbalance in these systems. Now, the point is that for the initial nil state, when I am looking at longitudinal dynamics, I find that MZ out, where there are initial upspins out here, they are all similar and they go to a superthermal value, while the other two goes to a subthermal value. Whereas for MX, essentially it turns out that these two, where I started from the upspin, are just opposite of each other. One of them goes to the superthermal value and subthermal value, and the other downspins do not oscillate much. And finally, for the initial vacuum state, the states on the even rungs are have essentially are equal. Their oscillations are equal, and they are exactly negative of the oscillations of the other rung. So it has a complicated spatial structure, and essentially that spatial structure is what gives rise to imbalance. So how do we see this imbalance? What we do is that we calculate both the long time average numerically, and also the diagonal, also this ensemble average, and see that they match. That's the first thing. And the second thing is that we define these imbalance operators. So for example, this imbalance operator starting from the Z2 state and for longitudinal magnetization is given by this sigma Z with plus and minus signs which are given here. Okay. So it's for up spins it has a plus, and for down spins it has a minus. And there are other such spin structures out here. And you see that for the initial nil states, this imbalance starts to grow once we move away from this Z2 from this delta equal to 0. However, for the vacuum state, the imbalance only starts to grow around delta equal to 0.5 and then moves up. And this is a finite size effect, all right, because for larger system size it comes down. So in the thermodynamic limit, it's going to vanish. But the point is that for finite chains, this is nevertheless standard imbalance. So around delta equal to 1, even in this otherwise ergodic and clean systems, I mean, this thing leads to this imbalance. So the other thing which is interesting about these cars, which tells us something about their origin, is can be understood from these fidelity oscillations. So we take this wave function overlap with the initial state and plot log fidelity with as a function of time. And also in the same plot, in the blue curve, we plot the Shannon entropy. Now, when I am at delta equal to 0, you see that the Shannon entropy drops both when the revival peaks and exactly in between this. This tells you in the FSA picture, you start from an upspin, which is this giant coherent upspin corresponding to the nil state. And in between, you go to another state, which is very, very localized in the Hilbert space. And that's why the Shannon entropy drops, which can be seen to be the Z2 bar. However, at delta equal to 1, the Shannon entropy drops only at the revival frequencies, but not in between. This tells you that this scarce-induced oscillation do not follow a simple FSA picture in the sense that it doesn't go between two Fock states. The state at the other end, is a superposition, and this has a pretty high Shannon entropy, which means that it's spread out in Hilbert space. Okay, so this sets this kind of scars apart from their standard PXP chain counterpart. And okay, so here is some pictures of these fidelity revivals as a function of delta. So you see that as I increase delta, this thing just goes down, and this is for the Z2 bar initial state. And here, this is at delta equal to 0, both of them. And here at around delta equal to 1, you see that this is the state for vacuum, and this is for Z2. And the picture is, again, qualitatively different. So this fidelity oscillation and the initial state overlap can be related. Essentially, you see, one can show that the states with maximum overlap, the difference in energy between them is what gives rise to this oscillation frequency. So we checked that, that's a more or less okay match. That one can understand these oscillations to be, the frequency of this oscillation to be the difference between the zero energy and the next excited state energy, this match. And then let me take the next 5 minutes or 2 minutes. Okay, so I'm going to finish in 2 or 3. So let me just talk a little bit about this chirality operators and their role. So here, this Rydberg lattice has 2 chirality operators, C1 and C2, and these are given in combination of this product of sigma z, this C, and the translation operators. And this tells you that both of these anti-commute with the Hamiltonian, and this tells you that there should be an exponentially large number of zero energy states, which follows from the index theorem. Okay. It also tells you that there is a E2 minus E symmetry in the spectrum. And what this does is that if you take these, expectation of any finite, of this matrix element between any finite energy state, you can show that that's equal to the expectation at between sigma z I plus 1 and A, that is shifted by one side and negative energies, okay, E going to minus E. And similarly here, and here it shifts to the other side of the ladder. However, for the zero modes, this doesn't hold because the chirality operators do not convert zero mode to another particular zero mode. There's nothing called negative of the zero mode. So it just takes you to another set of zero modes, okay? So the matrix elements of the spin operator in the zero energy subspace satisfies this. What does this do? So the other thing is that when we start from this Z2 state or its time reverse partner or the vacuum state, these have zero expectation value of the Hamiltonian, which means that these are infinite temperature states. And therefore, for these to happen, you see that the overlap coefficients with any finite energy has to satisfy this, okay? So psi 0 E mu must be equal to psi 0 minus E mu, only then this sum can go to 0. The point is then that you can show that these combined with the sign structure Oops, sorry, I'll just take one more minute. This combined with the sign structure essentially tells you that any contribution to this imbalance operator from the finite energy states just goes to zero. And the entire contribution comes from the zero energy state. Now the puzzle that we have here is, why is there an anomalous zero energy state which has overlap with some initial Fock state? And that is something we are not able to analytically resolve, but we understand this numerically that this too happen. Okay. A similar thing can be proved for X imbalance. I'm not going to get into the detail, I'm running out of time. But however, for the vacuum state, this imbalance has contribution both from zero and finite energy state. Okay. And this imbalance is really emergent in some sense, because neither the initial state nor anything else breaks this spatial resolution, spatial pattern per se. Okay. So, so it doesn't originate from a translational symmetry breaking state at t equal to 0. Okay, so that's the point. So now, in just 1 minute, let me just tell you about some simultaneous zero modes in this quantum many-body system. So suppose we consider a generic many-body system with this thing, with where H0 and H1 commutator does not vanish. So a generic zero energy eigenstate of H satisfies H. This whole thing acting on some eigenstate gives you 0. However, these modes are usually solution for a specific value of lambda. And if I change lambda a little bit, being mid-spectrum states, ETH predicts that you are not going to have any information about the nature of these states when lambda is changed, because no perturbation theory is going to work. And that's a consequence of the fact that near that point in the mid-spectrum states, there is an exponentially large number of very minutely gapped state near this zero energy state, and changing lambda essentially just creates a random superposition of the initial states. So the mixed spectrum states are usually ETH obeying. However, it can also happen that there is a linear combination of zero modes of H0 out here, which becomes a zero mode of H1. If this happens, this is a simultaneous zero modes of H0 and H1. And their existence leads to ETH violation, because here if I change lambda, there is no change in the structure of these zero modes, and therefore it violates this ETH prediction that any change in parameter is going to essentially randomly sort of mix these initial zero modes. And okay, and their existence have been shown in U1 lattice gauge theory by some papers by Arnav and Devashish sometimes back. These zero modes are not generic, and previously they haven't been found in a Rydberg chain, but here in Rydberg ladder we find some simultaneous zero modes, which are these zero modes with very low Shannon entropy. And the reason they have very low Shannon entropy is that typically it requires a very specific linear combination of the zero energy states, and they are well localized in Hilbert space. However, this doesn't mean that they are going to have a low entanglement entropy. Their entanglement entropy can still be a volume law. Okay. So, and these zero modes are some things that we find in this ladder, and we are still trying to understand their analytical significance. I mean, we are still trying to understand them analytically in some sense. Okay, so I think I'm out of time, and so I should stop. And so thank you for your attention.
Thank you very much. A very interesting talk, very informative. I have a general question. I mean, why would you expect ETH to be valid for a small quantum system?
It's not that small. We go into L equal to 26, and there the Hilbert space dimension is, I guess, of the order of 40,000 or more, something like that. And these are finite size systems, but just to answer your question, so if I were in, for example, delta equal to 0 and vacuum initial state, I see all predictions of ETH to come true. It's just only in these kind of settings in the same system size, I don't see this ETH, and that's the comparison. This car-induced violation of ETH is always a weak violation of ETH, and in the thermodynamic limit, it will be very hard to find any of this.
This quantity as well as the other things you are showing all look kind of symmetric with respect to equal to 0. Is that exact?
Yeah, that's because of the chirality operators. E2 minus E symmetry is here.
In the many body spectrum.
In the many body spectrum.
So if I think in terms of the Hilbert space graph for the Hamiltonian,
yeah,
is that bipartite?
Oh, does that translate to that?
I mean, why is it symmetric? I mean, thought of from the point of view of the
Oh,
Hilbert
because
space
this
graph.
chirality operator has
Right.
anti-commute with the Hamiltonian.
Right, right.
And
but if
then if there is a E, there has to be a
There has to be a
CE,
minus.
which is minus E, basically.
A related question is these anomalous zero modes you're talking about.
Yeah.
Do they live in a kind of a part of the Hilbert space graph that's disconnected from the rest?
No, the way we find it, so I really don't know whether one can think of it in that term. The way I try to think of it is that, you take this, the easy term, which is this Fock state term, I mean, sigma z, this thing, find out its zero energy modes, and there are a lot of them. And now, within the zero energy modes, using linear algebra, try to find out a combination, which is also a eigenstate of sigma x tilde with zero energy. And then you have found one, if you can.
Right.
And these are the zero energy modes that Moynihan found numerically.
And these are robust to lambda, like changes in lambda don't change them.
It doesn't change. So that's why I plotted it at delta equal to 0.5, where the other states are completely different, actually.
Right.
Also, there is this thing that we are still trying to understand this analytically. There is a spin 1 representation of this, and maybe something will turn up, but I'm not sure yet.
And what about disorder in the coupling, spatial disorder? Are these robust to that?
There are no, so we haven't checked that. No, we haven't checked that. Sorry. Yeah.
So thanks for the talk. So I understand that the Z2 scars, you don't have an analytical structure for them, or maybe you do. But
Z2 scars for the ladder. You mean for the ladder at delta equal to 1 or
delta equal to 1, yes.
No, delta equal to 1 we do not.
So,
because
and do you have any evidence that there is also maybe this spectrum generating algebra for the other type of scars? Or
no, sorry, I'll try to get here. So if we have a XY model, spin 1 XY model in the presence of this magnetic field, I know exactly how analytically to get this spectrum generating algebra.
Yeah.
The second thing I know is that if I have a Rydberg chain, I have this FSA picture.
Or even it's very close to BVCSU2.
Yeah, it's very close to that, but people typically do this in this forward scattering approximation. You know, there is some leakage, but you can still get some spectrum generating algebra. But here, the key point is that you start at one end from one of these Z2 state, and the other end, you go to another Fock state, which is Z2 bar. And you need to know these two to construct this FSA picture. For us, the other end, as I showed from this Shannon entropy and the overlap out here, let me just show you this. Yeah, so you see here, this is for the delta equal to 0, where it's like the Rydberg chain. Here, the Shannon entropy drops at the middle, which means the other end of this FSA picture, where this progression terminates, that's also a Fock state. However, in our case, there is no such dip, which tells me that the Shannon entropy at the other end of the spectrum is large, which means that it's a linear superposition of many Fock states. Okay, its entanglement is still low, otherwise it's not going to have some overlap with the initial Z2 state. But the point is that its Shannon entropy is still this thing, and we do not know what that state is analytically, and that's what is the problem in constructing an analytical picture here. Trying to do some guess, but not successful yet. Yeah, Dipti Manda.
So, one question is, you say the scars at delta equal to 0 and 1 are very different. So, is there some crossover as you vary delta?
No, the scar induced. So, okay. So, so you see around. So, as I start from delta equal to 0, this is magnetization oscillation. Okay. So, these oscillations decay, and eventually at delta equal to 0.5, it just vanishes, everything is ETH obeying. And then it reappears again.
Right. So maybe 0.5 is the crossing point.
Maybe it's not so clear, because these oscillations go down, and I'll show you another plot here. You see that from delta equal to 0.05 to 0.25, these steadily decreases. Around 0.5 it goes to 0. and then it again reappears around 0.7 and goes till 0.1, till 1, sorry. So I'm not sure whether to call it a crossover, but it certainly seems that delta equal to 1 is, larger delta is a special point where you see this kind of oscillations.
So I had one more question. So this star states at zero energy that you're talking about. So many systems there's an index theorem which tells you that
Here also.
you do have an
Yeah, that's because of the chirality. So I have two chirality operators here. So, the Hamiltonian anticommutes with both of them, and there is an exponential number of zero modes because of the index theorem.
Okay, so let's thank Krishnendu.